It's my pleasure to introduce you to Kuang Xu. He's a tenured associate professor at the Business School of Stanford and also, by courtesy, associate professor with the EE department of Stanford. He holds a bachelor degree in EE from 2009 from the University of Illinois at Urbana-Champaign and a PhD in EE in computer science 2014 from MIT. Well, his research focuses on understanding fundamental properties and design principles of large-scale stochastic systems using tools from probability and from optimization. And most recently, he got interested in exploring the interplay between stochastic modeling, information, and learning, very close to the theme of this workshop, I suppose. And that is a theme related to the topic that he'll be talking about today. So, Kuang, please go ahead. The floor is yours.
Thank you, Michelle, for the general introduction. And great to see everyone, good friends from the community. I know we're back to non-virtual, but still sometimes it's nice to be able to meet everyone without having to fly around. So thank you. And the talk is supposed to be somewhat interactive. I'll try to go a little faster. So if you have questions, do raise your hand, and we'll try to make it as fun as the format will allow. Okay, so here we go. Just a quick preface, I did give a talk roughly of this content back in the Stochastic Network workshop. So I apologize for those of you who already see that was there. But hopefully, maybe I will have more experience presenting this, and maybe there will be something interesting things coming up. So just as a preface. So today's talk is about a sequence of two papers I've kind of worked on recently with a postdoc fellow now, Gal Mendelsohn, who got his PhD from Technion and actually joining Technion this fall as this spring as a professor. So a lot of work that really goes to Gal, and there's also a recent SNAP seminar where he focused on the second part of today's talk. So I won't go over that too much. But the general idea is to understand information design for resource allocation. And the talk will essentially divide into two parts. In the first part, I'm kind of thinking about how would you utilize the information, curate the correct information so you can perform effective allocation. And the second part kind of flips on this head, which is how would you actually design statistical methodologies for a system that already has some non-trivial resource allocation algorithm running. And we're still trying to figure this out, how to frame it. So the talk might be a little bit of exploring this new territory, and obviously any feedback will be much appreciated. Okay. All right, so as I said before, there are two parts. So specifically part one, I'm going to talk about load balancing under sparse communication. Some of the algorithm I will talk about actually was covered by Rhonda just now. The second part, I will look at a statistical inference in controlled systems. And a unifying theme here is the notion of kind of thinking about information more rigorously, maybe in a less ad hoc way. And that's the hope. All right. So let's jumpstart the first part. And I guess for this community of queuing theorists, this has been a very, very central problem in the last 20 years, which is how would you essentially allocate resources that come to you as a decision maker to be processed at a collection of distributed service centers or servers. So the canonical problem is called load balancing, where a decision maker dynamically directs incoming jobs to be served at different servers. We have a lot of industry interest in this when designing data centers like Elasticsearch and stuff like that at Amazon. And also you can find similar models in call center, healthcare, and manufacturing. Now, for today's talk, my main focus is going to be on data center. And the reason will become clear, where the requirement for information is incredibly high in that kind of applications, meaning that you're operating on such thin margins and such a high speed that you just cannot afford to make a phone call to the server and get some idea about the service time, the load. So that will be sort of the running example, which is load balancing in data centers. All right, so schematically, here's a picture we have. Jobs arriving, let's say, according to some stochastic process to a load balancer, and upon arrival, immediately gets routed to one of the K available servers. Each server has a queue, and jobs await there until it's being serviced. Now, in this problem, the service times are stochastic, and therefore the load balancer cannot easily predict how long the server will be, how long the queues will be at those servers without essentially asking them at some point. Okay. And then when the job is complete service, it leaves the system entirely. So we are not considering some kind of network thing. It's just a one hop and you're gone. All right. So the high-level goal for this type of system is the load balancer wants to distribute load evenly across all the servers at all times. I mean, for obvious reasons. If not, then the performance will be very good. So it's really paramount that the load balancer has reliable access to all the servers' state information, state of the congestion. And in our example, you can think of them as just the queue length at those servers. However, to maintain such perfect information can be quite costly. And I will show you later that to get this information exactly right at all times requires on the order of one message, one communication per job that ever shows up to the system. And you can imagine as the system scales, if K is very large, then this is quite a bit. So every job I need to send a message to someone, and that's not so great. So the focus of this talk is really trying to drive down and hit the bottom, hopefully, of just how much can we do with performance if we only have a very sparse information exchange. So squeezing as much performance as possible out of very sparse information exchange. Okay. All right. So now I'm going to actually do a brief review of the literature. And in fact, this problem has been thought about in various angles in the past. So I will kind of try to illustrate what's different in this paper. And a couple of disclaimers. It's a very incomplete review. There's a huge literature on load balancing. And here, I will mostly focus on the most representative ideas and examples. So I apologize in advance if your papers are not being cited here. And also, I will only look at the focus on communication. So there are many other aspects about how to characterize performance in various policies, which I will not look at. I will exactly look at how people think about communication and information exchange. Okay. Any questions so far? Take a breather. Great. All right. Okay, so the whole literature starts with this celebrated algorithm called the join shortest queue, which till this day, assuming the service times are homogeneous, it's considered the gold standard. So if you have perfect information, you see a job, you look at which queue is the shortest, you route it there. And obviously the downside is that it requires full state information, or at least which queue is currently the shortest, which is sort of like full state information. Okay. Now, one of our first algorithm to realize, hey, JSQ is great, but it might be kind of hard to implement, is this line of work called the power of D choices, which we all know very well. And it starts from the seminal paper by Vidinskaya et al. In 1996, and around the same time by Michael Mitzenhamacher in the US. So Soviet versus, well, actually not Soviet anymore, but Russia versus the US around the time. And there's been hundreds of papers about that. So it's a very popular algorithm. The idea here is if the job arrives, the load balancer queries D servers at random, and then routes the job to the shortest among the D server. Okay, so it sounds really cool. And you don't have to ask everybody, you just ask a subset of the servers. Now, we know that it does perform pretty well, even when the number of servers is large. However, I do want to do some accounting here, which is just exactly how much information is required to run this algorithm. And you notice that because every time a job arrives, I ask the D servers, and to conduct such communication, you actually need to send D messages to D servers, then receive D messages back from those servers. So all in all, for every job that arrived to me, I will actually spend 2 D messages throughout the network. Okay, so that's actually not so great. It's better than asking everyone, but still 2D is quite significant. Even if D is 2, that's 4 messages per job. Okay. All right, so it turns out the true communication burden of JSQ wasn't as bad as we initially thought. So when Power 2 was proposed, the idea was instead of asking everyone, I ask only 2 people every time. But it turns out, as was pointed out in this later paper, Liu et al., that you really need only 1 message per job to implement the perfect route to shortest queue. So in this version, the insight is that because only service times are unknown, essentially, in the setting, so all the server needs to do is that every time the job departs from its own server, sends 1 message to the load balancer and say, hey, the job you sent me back then, now it's gone. So that's all you need to do. So if that's what's happening, then we really just need 1 message per job to get the perfect stated information correctly. Okay. So this kind of goes to show that even though there are many other reasons to potentially deploy Power 2 choices or Power D choices, from a fundamental communication level, it's actually not the most efficient thing. So this also suggests that if we are talking about really sparse communication that hits at the level lower than that JSQ, we're really talking about a fraction of one message per job in order for this to be really scalable. Okay. All right, so let me just do a very quick summary of the state of the current literature. That is that in order to, skip this a little bit, in order to get the perfect state of information about the system and run JSQ, I need one message per job. Power two choices for some other design criteria, potentially. They actually use slightly more than that. It's 2D messages per job, so it's not really sparse. And a policy called join the idle queue that's proposed in the same paper by Lu et al. It actually has pretty decent performance under moderate load, not so great under heavy load. In fact, it's not even stable in many cases. Requires slightly less than one communication per arrival, but not by much. We're not talking about 100, 1,000 times less than that. Okay. So all in all, to say that even though existing results suggest that maybe some kind of sparse communication pattern could go a long way, but we don't really see evidence yet that we can do very well with truly sparse communication that is much lower than the baseline. Okay? And another aspect of this literature, once you kind of wade through it, is this feeling that maybe by style and by habits, oftentimes we discuss communication protocols along with a routing algorithm fused in one. So power two choices is actually both a communication protocol of probing different queues and a routing protocol that you only route to the latest queues that you probed in a certain way. And if you think about this kind of philosophy, it makes it very difficult to really make progress on either side without touching the other. So for example, in practice, if you want to change a routing policy with the way things are done, you have to actually rewire the whole communication architecture as well, which seems quite clunky. It's actually a challenge. All right. And also for the same reason that the literature so far has been focusing on understanding specific heuristics, such as GIQ, JSQ, power two choices, and there hasn't been as much work devoted to understanding some kind of fundamental trade-off curve between communication and the achievable performance. So ideally, if you think about the really bottom line, you want to draw a curve. This is how much communication budget you have, and this is how much performance you can get. And we don't seem to be very close to that state of affairs. Okay. I sort of took some time to motivate this, but I think it is important because I think it's important to kind of understand where we are in this field, and that's sort of my personal opinion on where things stand. Okay, so the question we'll hopefully answer for this part of the talk is, can we use sparse communication to achieve good performance in load balancing? And if so, what are the type of key insights that might enable that? All right. So the proposal will be called CARE. It's some kind of a acronym that we think fit very well. But a key idea from this proposal is to use state approximation as a virtualization layer, as an information intermediary. Okay, so specifically, we're going to present a model for study load balancing with sparse communication. And we're going to use state approximation as an intermediary in the following sense. The load balancer will first estimate the state of the queue length via a communication protocol. Once the state of queue length is being approximated all the time, then it will feed the state approximation into some kind of policy to decide where would you send the next job. So it sort of decouples the estimation part and with the decision-making portion. Okay, so to make it more concrete, here's what I mean. For instance, if you have a server has a queue length going up and down as a blue line, then I will implement some kind of approximation on the side of a load balancer that tries to guess what the blue curve is. So for instance, in this particular case, orange curve is approximating it, and it has an error of 2. But let's say I'm a bit more lenient. I can allow the approximation to be more erroneous, error of 3. Then on the right-hand side, you can see the two curves sort of differ a little more, and the shape kind of doesn't match as well. So essentially, in my world, the orange line is what the load balancer will see, and the blue line is what the reality happens to be. Okay. All right. So now this CARE model is going to have 4 components as a conceptual kind of model. The first component is communication, which specifies how and when the servers send messages to communicate with the load balancer. Approximation, how the load balancer generates an estimate of the state. Allocation, which is how to route the jobs according to such an approximate state. And finally, the specification of the underlying stochastic environment, such as various primitives, arrival rates, service times, and so on. All right. Okay. So with this framework in mind, maybe let me briefly mention why we chose to use state approximation as sort of like this cut into this messy problem. So one obvious reason is that using state approximation is the type of abstraction that will allow you to decouple the communication estimation module of the algorithm from the load balancing part of the algorithm. Okay? For instance, one might hope that once we can guarantee decent approximation, we can then subsequently guarantee decent performance as well. And in fact, in recent years, we've seen encouraging empirical performance of such algorithms that actually do indeed make use of state approximation at its core. And here's some example of that. All right, so, but there's also a conceptual benefit for using state approximation as an intermediary. So in particular, earlier, I kind of mentioned that we have this kind of holy grail of understanding communication to performance link in some fundamental way, but that's very hard to articulate because it's just really hard to draw a link of, let's say, 5 messages per second to the type of policy you can design using 5 messages per second. However, if you actually insert in the middle the creation of approximation layer, then the question becomes more tractable. So first we can ask, what kind of fundamental limit can we hit by using approximation with the most limited communication? And the second question is, given a certain approximation quality, what kind of performance can we hope for? So at least provide some practical blueprint for us to start kind of chopping up these problems and tackling them one by one. Okay, so that's essentially the motivation behind it. All right, any questions so far? Great. Okay, so maybe let me talk about some results that we have so far. Okay, so the results will be divided also into 2 parts. One is what kind of communication protocol that leads to approximation can we hope for? How efficient can they be? And second is once we have some kind of approximation guarantee, can we derive some sharper understanding on the type of performance we can hope for? So the first main takeaway concerns the communication to approximation link. I would say the main message we want to send here is it is indeed possible to achieve good approximation, but maybe the surprise here is the quality approximation with how little communication you actually need. Okay, so we will analyze 2 communication approximation schemes. And for both cases, we'll parameterize the quality approximation by the error of X. So when I say X, it means that at all times, deterministically, the perception of the load balancer of a certain Q never differs from the actual Q length of that Q by more than X. It's a deterministic bound. It could probably be relaxed to stochastic bounds to be even, allowing even like more efficient characterizations. But just to show you that right now there's nothing behind the curtain. If it's X, the error is at most X. Okay, and when you have this type of system, what we see is that you can see results of the following kind. Under one scheme, we can show that for a particular error X, then the number of messages per arrival scales as 1 over X plus 1. By scale, I mean like exactly at most by this number. And for another scheme, which is more advanced, it actually does even better. It's 1 over X times X plus 1. Okay. But the main message here is that in both cases, when X is just reasonably large, you see a really, really big drop in communication. So for instance, if we look at the baseline of 1 message per job that was used to approximate the perfect Q length, then if I allow an error of 2, then I can actually reduce communication by 83%. And if I allow an error of 3, I can reduce by 92%. And these results hold over all loads, and not just in low traffic. So just to put into perspective, 3 seems like a pretty benign and small number if we consider a heavy traffic theory when all the queues are blowing up to infinity. All right, so here's a picture of how things look depending on the loads. Even though the bounds actually are loads independent, here what we see is that as the approximate error gets into 3 or 4, you're really looking at like a 95% reduction in the level of communication that you need. Okay, So to kind of back it up with more theory, the main theorem in this part shows that the load balancer achieves sorry, actually, this is not the theorem I'm thinking about. But anyway, so that was the part where we were talking about the approximation quality. So the second part is to kind of ensure that once you have a good approximation, you also get really good performance. And here we actually have to develop some new tools that has to do with subdiffusive stasis collapse. So here, essentially, the punchline is that we can show that once you have a decent approximation quality and under the appropriate diffusion scaling in heavy traffic, then indeed you are very close to optimal. Now, this part is not entirely surprising because you would expect that when your approximation is good, your algorithm should behave more or less like a JSQ. I guess here it's just that we can actually drive the same result when approximations are fairly crappy. So I told you before that we can reduce communication by about 90% if you only allow 2 or 3 units of error. But to get a good performance here, you in fact can allow for much higher moderate error. So all in all, kind of like combining these two results, we're really showing that good approximation is possible with a very sparse communication, and decent approximation already leads to good performance. So together, the link is sort of complete. We actually can get incredibly low delay and good performance with very sparse communication. And this can be backed up by the theory entirely. Okay. All right, so far it's about the theory part, and that's a very good sanity check, but we were still curious, does the same kind of like hope really carry into practical applications? And for that, we try to do some simulation with the real systems here. So here we're simulating a 32 system. It's not actually that big. We're not really looking at thousands and thousands of servers. It's a relatively finite system. And here we're looking at the CCDF of the latency in steady state. So maybe this plot sort of says it all, in the sense that I'm plotting each line as a sort of a level of communication, and each line is sort of the best algorithm that we can find that hits that level of communication. So 32% would suggest that this particular policy uses 32% of communication compared to the JSQ benchmark. Okay, so if you see that JSQ is right here in the blue line, and the next line right here, orange, uses 30% of the communication, but actually hits really, really close. So to put things into perspective, the power of 2 choices, which uses 4 messages per job, essentially way out there. So it's actually quite far from the optimal performance. Now, if you go further up to round robin, all the way out there, you can see that even with 99% saving in communication or 95% saving in communication, you still see a huge drop in latency. And notice that this is plotted in a log scale. So if you see a clear separation here, there's a pretty big exponential reduction in the tail probability that's being plotted here. Okay, so this is at a relatively heavy load of 95. All right. So this is just to kind of motivate the model that we've been looking at. And maybe here I will give a little more detail on how we actually do the approximation and the type of result we'll get. So formally, we're going to look at a system in continuous time with a single load balancer and K servers. So servers process jobs in a 5-fold manner, first on, first out. Arrivals follow a renewal process with constant rate lambda. We don't actually need a Poisson here. And service times are IID with each server, but they can have different rates across servers. So server I will have a rate mu I and may vary across I. Okay. Now, when we talk about communication, here's the realm that we operate in. So servers may initiate communication at any time by sending a message to the load balancer. So every time I send a message, we'll assume the message contains the entire current queue length at the local server. We're not looking at the number of bits because that's typically not the bottleneck here. Now, the approximation algorithm, they use the entire history of the received message to estimate the state, and we'll assume the state is 0. And the approximation was accurate to start with. The load balance algorithm will only look at the one where it simply looks at the approximate state and then send the job to the lowest queue in the approximate state. Okay, so here's on the approximation design. So the basic estimator is simply set the approximation to the latest reported queue length on the load balancer side. And we actually are advocating for a little more advanced version of that, which is that we're going to use an emulation-based algorithm. Namely, from the perspective of a load balancer, for every arriving job, I will actually generate a predicted service time for that job. Then I will send it to some queue. And then in my head, I will start emulating when the queue might see the next departure. So for instance, the simplest thing you can do is for every job that you get, you just pretend the actual service time is equal to its mean, which is obviously incorrect. But again, that's just an emulation. So you can kind of still pretend that's happening. So we call this MSR, the mean service requirement approximation. So essentially, I will simulate as a load balancer for all the servers and pretend that each job there has a deterministic service time. So I can use that to calculate when the next departure might happen. So kind of emulate that. And there's a more sophisticated version which kind of truncates this emulation after X minus 1 job departures, because the idea is if I haven't heard back from the server for a long time, maybe there'll be too much noise and bias. I'm just going to cut it short and stop doing any emulation. I will just freeze the QLED and that will be it. Okay, so that's how I approximate as a load balancer. Now, on the server side, how should they communicate to me? We consider a few versions as well. So RT is the simplest benchmark, which that server just sends deterministic messages every essentially a couple of seconds. So every R seconds, every 1 over R seconds, I will send a message, and the rate is essentially R. Another one is departure triggered. So here server will send a message after every X departures. And finally, the last one is probably the most interesting one, which hasn't been considered much in any literature, which is error triggered. So in this case, the server will actually send a message every time it thinks that I, as load balancer, am too wrong about its state. It's a little convoluted, but the key insight here is that in this particular system, when load balancers coordinating with servers, we have a information asymmetry. So the server obviously knows its own queue length, but the load balancer only knows half the story, which is where the jobs went. However, from the server side, I actually can know exactly what load balancer thinks about me. So I will use that to drive when I send the message. So as a server, I can emulate what the load balancer thinks my queue length is. And whenever that error is too big, departing from my actual queue length, I will send a message say, hey, right now, let me refresh you and tell you what the actual queue length are. Okay? So this is the so-called error-triggered communication mechanism. All right. So with these 3 schemes in mind, here are the results that we have. So for the average rate of communication, the average rate of communication gamma is given by the following, which is that if I use DT, deterministic, the departure triggered, and every X jobs I send a message, or I use error triggered, every X error I send a message, and I use the mean service requirement as an emulator, as a load balancer, then I can guarantee an error of X, and I can guarantee a communication rate of lambda divided by X. And this holds for any general job size. Now I can do better if I make some distributional assumptions. So if I assume the job sizes are exponentially distributed, then I can actually show that using this adaptive error trigger communication rule, I can get a much, much smaller scaling, which is mu over X over 2 minus 1 squared. So the key here is that X now is actually a quadratic in the denominator, so I get a much faster drop off of communication rate. And finally, I'm willing to assume that some kind of heavy load so that the queues are not empty too often. This is relative. This is mostly a flaw of the analysis, I guess, but I can get even a stronger sort of numerical bound here that even performs well when X is very small, like 2 or 3. Okay. So the numerical plot I showed you earlier was plotting this particular bound that actually is very tight compared to the simulation results. All right. And this is a slide just to show the other side of the theory, which is that when we go from approximation to the performance, we achieve the result I told you as follows. So here, what I want to show is if I have a reasonable quality in approximating the state of my servers, then on top of that, I apply join the shortest queue. I want to know how well do I actually do. So to tackle this, we have 2 types of results, and together they give this final result. Okay, so here I'm going to consider a regime where the arrival rate and departure rate both scale linearly in n, where n is sort of a scaling parameter. So for example, if I have 30 servers, then 30 will be fixed, but the speed of each server will sort of grow as a server pool. Okay, so in this particular regime, we're actually going to say the result not necessarily relying on a heavy traffic assumption, but the following result will be true if you are underloaded, critical loaded, or even overloaded. Then the following will be true. That is, first, whenever the approximation area is at most root n, or little over root n, then I have a form of state space collapse, namely the maximum difference of the queue length across all the system, all the servers in the system, will be on the order of root n or smaller with a high probability. So it does imply that whenever you have a good approximation, it tends to equalize the queue length. Now, the second part, but so far it's only the queue length. I haven't really gotten there yet. Then the second part is to show that once you have this kind of diffusion scale balance or state space collapse, then I achieve asymptotic optimality compared to any other algorithm that you could conjure up here. So if SSC holds, then the total workload in the system across all queues is within the optimal workload, again, by a root n factor. Now, because my system kind of scales in order n, this is actually a management factor with respect to the scaling of the entire system. Cool. All right, so now I will show you a few more simulation results in a similar spirit of the ones I demonstrated earlier, but now hopefully with more kind of a granularity and just cover more scenarios. So again, I'm going to run 30 servers in discrete time. Each time slot, a job will arrive with probability lambda. Service times are geometric with the mean 1 over k. So I'm not looking at heterogeneous servers here. And each server completes 1 unit of work at every time slot if it is not empty. Okay. So this plot I showed you earlier, I probably won't go over too closely again, but just it goes to show that the upper bound that I demonstrated in the previous slide is quite close to the actual performance. The actual performance is even better as far as how much communication you need. Okay, so a plot like this is sort of more interesting. So it's a plot where I not only show you the performance, but also what kind of communication schemes are deemed most optimal in achieving this law. So here I will look at different communication burdens relative to JSQ. But for each level of communication budget, I will choose the best policy to show you, and I will tell you which policy it was. So what's kind of interesting here is that, again, like the scheme proposed here do very well. But what's interesting is when the communication gets a little sparse, gets to like a sub 15% of the total communication, you see that this emulation approach on a load balancer side using a mean service requirement, plus this adaptive error-triggered communication protocol becomes essentially the winner. Whereas if your communication budget is very abundant, you're not very constrained by communication, then potentially some other more basic way to do it can help reduce variance and potentially it's a little better. And it turns out this insight is actually quite uniform across loads. So now the load is a little lower. We see that all the policies tend to get a little squeezed because load is about 80%. You still have a pretty big performance boost by using the sparse communication schemes here compared to, let's say, power of two choices, which is somewhere in the middle here, and obviously round robin. And finally, if you have a very little load, it's about 50%, then the lines get even closer. But what's kind of interesting here is that when load is very small, somehow it's more important to use these more sophisticated approximation schemes and communication schemes. So here, MSR and error-triggered communication basically dominates all the way down here. Cool. So I guess the punchline we'll kind of learn from communication is that the simulation is that very sparse communication can still deliver superior performance that is, I would say, nearly competitive to JSQ, not exactly like JSQ. But for communication under the 15% benchmark line, we find that MSR plus the error trigger combo really dominates at all traffic levels. So if I have to go to implement this in practice, I would probably start with having this emulator on the dispatcher side and have this kind of error triggered communication on the server side. I often get a question talking about this topic that people might think this emulation seems very intensive. But it's actually not. It does not involve any simulation. There's no Monte Carlo It's simply a deterministic rule with which the server will calculate what the queue length are. So that's a great thing. Under moderate or small load, they're still sizable, but much smaller gay. And in those cases, actually, most of the adaptive policies behave about the same as round robin. And intuitively, maybe when the loads are not very heavy, you probably should just use something very simple, do some kind of round robin allocation, and don't bother with chasing around the state information. Cool. All right, so I guess a summary for this part of the talk is to say that high performance allocation with very little communication, I do still think is a very important problem, and probably gets more important as we're driving these very heavy ML driven workloads. Existing methods use less communication, but we should be able to go much, much further. And that's sort of a belief that's being reinforced, at least on my end, having seen the results here. We use this framework called CARE to probe the limit of what's possible. And the hope here is that to kind of give some conceptual clarity on how to attack this problem, namely by using approximate state as an intermediary to separate out a communication problem from that of routing. And that's something I don't know what's going to fly in this community. So far, I haven't seen much, but I think that's at least a viable plan of attack here. Now, is approximation the right way to approach the problem? I absolutely don't have a claim on that. So far, it's the most intuitive way. We figured out how to kind of truncate this complicated link between information and performance, but maybe there's other way to do it. And also, we've kind of touched upon some fundamental limit. For example, the optimality result that we showed, at least it's one side of the story. We know what it takes to be optimal, but would it take even less than that, or can we do something better? That we don't quite know yet. So we have some kind of positive results. We don't have enough negative results at this moment. In fact, we have no negative results at this moment. Let me put it this way. So both results on the communication and on the performance are essentially upper bounds. And I'd love to hear how to understand that their optimality themselves. Great. Any questions for this part? Yes, Amy.
I'm curious, like the approximation teams seem to treat all the states kind of the same, but I can imagine that some states, like the idle state, is more important to signal back to the scheduler. And I was just curious if you had any thoughts on, like, is that a good idea? Like making sure I signal the idle state rather than just how much error there is?
Yeah, that's a very good question. That's a super good question. I think the answer is yes. I think there should be a lot of value in weighing the states differently, right? For example, if you know a queue is very long, you're just not going to send it there. And you don't really care if it's like 100 plus 2 or 100 plus 3 versus a queue that's like 0 versus 2 seems pretty important difference because you don't want them to idle. That's a very good question. Now, when we try to do when formulating this is initially we try to do something fancy, honestly. But one thing we realized is that the relative importance of the states, I think this is by itself is a very interesting theoretical question. It's a very load dependent. So whether or not you're catching the longest queue or whether or not you're catching the shortest server actually depends on load. So as the load of the system changes, sort of the relative communication importance shifts around across the state, just as an intuitive thing, right? So for example, if the load is very low, you absolutely better capture the idle servers. If the load is very high, most servers are busy. Sometimes it's actually pretty useful to just know a few intermediate servers. So at least you're not routing to the busiest server at all. So I think there's some notion that the importance of the state actually shifts as a function of the stochastic dynamics. And right now, absolutely, we have no idea how to even nail that down. Like, is there even a folklore saying idle states are more important to communicate under low traffic? Intermediate states are more important to communicate under high traffic. We actually believe there might be something like that, but we have no idea how to articulate that. So anyway, long story short, we went for the easy way is just at least can prove something for this uniform one cut fits all thing across the whole queues. But I'd love to hear if anybody has ideas. So.
There's a question by Tejas.
Yeah, so you have your load balancing policies look at the queue length metric. So I was just curious if most results would hold true if you start looking at workload. So you're doing joint shortest work or joint shortest work D. I mean, it also has a connection with replication, right? So redundancy with cancel on start is essentially
absolutely. That's a very good point. Yeah, I think we're looking at queues in part because the heaviness of the state space collapse is a little easier to do there. So I do think there's definitely an analog with workload. For example, one of the key ideas here is the error trigger, right? Because you can still do the same thing with a workload, because I can emulate what they think of my workload is and do that. So that part won't break. And I think intuitively it should go through. I'm just wondering if the math part will be harder. But I think as far as applications, it's actually quite important. Like you said, in some cases, like workload is much more indicative of what you should do versus a queue length. Absolutely. I think the idea here hopefully is general enough to carry through.
Right. The only drawback with replication is now, apart from the communication overhead, there's also this added overhead of canceling replicas.
Right. And yeah, and then like, how can you predict if something gets canceled or not? Yeah, that's actually another interesting question, which is right now, the only driver of error in my system is the departure, right? So if someone departs, that's it. But if you have a replication, when one job departs, you might cancel another job in some other queue. So that triggers another layer of things that you need to communicate, which is not here. But maybe that's okay, actually, because the other server can take care of its own communication. So that might be okay.
Right. And a quick follow-up. So you've been looking at bringing down the communication overhead, right? So what is the state? I mean, what is known about when there's absolutely no communication? I mean, if you look at it from bottom up, is round robin or random routing, is it all the same? I mean, what is the lower limit?
It's not the same. But this is probably well known as a folklore, by the way. I don't know if people know this, but I think that people probably do. They're not the same. A round robin generally performs much better because the typical idea here is that you do not want to introduce additional randomness to what you already have to deal with. So if you have no adaptivity, like you definitely don't want to inject additional randomness to how you route. So the better thing to do is just go round robin in some kind of intelligent way. That would be my guess. Right. But no, we do not look into that direction in this part.
Good, thanks.
Cool. Actually, it does show up in the second part, so that's a good question. I might mention that. Cool. Okay, so we're moving on to the second part. I want to do a time check. Michelle, I have 10 minutes, 10, 15 minutes.
Yeah, you have little less than 15 minutes. So
okay, so let's say I aim for 10 minutes. I think that'll be okay. So we'll leave some time for buffer. Great. All right, so far we've really been looking at squeezing down communication using as little information as possible to do decision making. So I'm gonna look at the flip problem now, which is I have a dynamical system. In fact, the exact same system, load balancing, but I want to learn how the system is doing. And I want to do some of the diagnostics. And I hope to illustrate some principles here. Now, unlike the first paper, we have a working draft, which you can see the link at the end of the talk. But I just want to press the saying this is even more sort of out there. I don't have as much mathematical formalism, but hopefully I can communicate the kind of a sentiment here and get people excited, if I may. All right. So this part, I actually want to switch gear and think about performing statistical inference in a controlled service system. Obviously, inference is a key word here, but another interesting aspect is the system is running some kind of control policy. One application that we kind of looked around, one of the most important one, is sort of health detection of a service platform. So for instance, the server might malfunction or slow down or in distress, and this kind of a job start to kind of slow down in that server. And in this case, maybe the computer failed, or maybe the human agent is under distress. It's not answering calls as quickly as possible. So as a decision maker, I want to be able to identify the identity of such a slower server. It seems like a simple enough thing to do, right? So the broader research question is how to detect from the observable of my stochastic system some kind of persistent underlying change in a critical parameter. I want to do it relatively quickly. I want to do it robustly. And here, we actually got to use the same schematic, which is that I'm performing inference as a decision maker, or in this case, the controller or load balancer. And I will use Q length as my historical data to perform such inference. So the procedure that I will kind of go with is that I will continuously collect data through some rule over some kind of batch of a window. And I will compute some summary statistics, so kind of reason about it. And then I will have a rule that I look at the statistics. If it triggers some alarm, and I would just say, hey, somebody failed, and this is the person that failed. Okay. And I want to statistics that are computation lightweight, so intuitive, easily interpretable, and also robust to load balancing algorithms and services disciplines. So probably not overfitting it to a specific load balancing rule and so on. So that's kind of the general high-level idea I want to go with. All right. So let's say we have a server that's slowing down. And the first question is, hey, why do we need anything fancy? Why don't we just directly estimate service time? If the service time is too long, then I declare the server slowed down. Well, turns out service time as a concept is pretty restricted. And oftentimes it's only meaningful when you have a special case processing discipline, such as FIFO. And it gets very awkward to do when you have processes sharing and stuff like that. Now, candidate number 2, which is actually what people typically do in these systems, which is using congestion data as a signal for the failure of services. So for example, you will use some kind of time average queue length as a key statistics. If you have a lot of queues piling up, probably a bad thing happening at the server and vice versa. So it's very easy to compute and interpret and intuitively appealing. It seems like a slower server should have larger queues. But the question kind of we want to ask is, does it work? And is it robust? Is it the right way to think about the problem? Okay. So this is like a quick exercise or a game that I play when giving this talk, which is to say that can you catch the bad guy? So here I'm actually showing you the historical sample of sort of like a sliding window. So on the x-axis I have about 30 servers, and on the y-axis it's their queue length during some kind of a window. And I'm just showing you a sliding window across time. So from 0 to 8, it's like over time. And can you tell me which server failed and during which window did the server start kind of failing, right? You can stare at it, but I guess the main point here is that you can probably see some peak here and there, but it's not super obvious, right? It seems pretty chaotic. And it's not entirely obvious. If I had to pick, probably this middle server 15 seems pretty high. But if you're a statistician, it's like the confidence is not very high. Okay. Anyway, so what's happening here? Queue length seems to be useful, but it doesn't seem to be very reliable unless you average over a very, very long time. Now, actually, not surprisingly, if I show you the same system, but simulating over a long time and looking at the marginal queue length distribution, you can see that the slowdown server has a slight bump at 2 as far as the distribution is concerned. But again, if you just stare at this thing, you really don't notice that something is wrong. It seems like everybody's pretty much the same. Okay. So what's happening here is that I'm actually showing you a system running under JSQ, my favorite algorithm in the first part of the talk. And for whatever reason, you see that the slow server is not being very well represented in the queue length data. It does not really pop out. Okay, so again, another picture here is that if I look at service, the queue length distribution, and I start the whole system with a broken server. So the server has a 20% slowdown when it's broken. And you can see that it took a long time for this bad server to really show up in the average statistics of the queue. And that's just another example to show that this is something is going on. It's not a great idea to use average queue length. Okay, so what's wrong with using average queue length? Number 1, it has a lot of variability. But number 2, what's more interesting here is that it tends to have actually some kind of information erasure whenever you're using a control algorithm. So in this case, you have adaptive control that's trying to balance jobs across servers, but you realize the very algorithm that tries to equalize congestion inadvertently erased as a result of its action which queue is congested. Because if a server slows down, it simply stops getting jobs and it starts to get fewer jobs. And as a result, their congestion level looks a little better than what the actual reality turns out to be. Okay, so and therefore information erasure turns out to be a pretty fundamental thing that happens not only under GSQ, but in fact under any throughput optimal and therefore necessarily adaptive load balancing algorithms. Okay, so what's our proposal in this setting? Noticing that we propose that we use actions as a key statistics and not the queue length, at least not the average queue length per server. So because the agent records the routing actions, then they can perform a statistical test by looking at the fraction of jobs that's being routed to each server. So if you remember this plot I showed you earlier about which queue is how long at what window, if I were to actually show you the same window, but instead of averaging queue length, I just show you empirical distribution of which fraction of the jobs went where, this is what you see. Okay, so obviously until Windows 4, sort of every server is about the same, but suddenly basically server 15 got shut down. You just don't see any jobs going there anymore. And you can derive a much more rigorous statistical guarantees for this type of estimator that's really sharp and way outperforms the other. Okay, and the same picture before, detecting queue length took like 30,000 time steps, whereas detecting through action really, really fast. Okay. All right, so the reason action does well in this particular setting is that not only does it have a small variance by definition, but it also is the kind of the destination of the information erasure in some kind of ironic sense. So by being adaptive, a policy sort of equalizes the queues, but the trace of their crime or action is actually recorded to the routing frequencies. So information sort of got transferred from the congestion data of the queue length to the action data of what the load balancing did. So kind of recognizing that, we realize action is a much, much better candidate in performing statistical inference here. Okay, great. So far, I essentially give you a very concrete example of why some type of a conventional, often used congestion measure isn't a great thing when you're deploying adaptive control. Now, it might sound a bit arbitrary, sort of we jump from one measure to another measure. So let me broaden up a little bit on where these two schemes sit, the two kind of pictures I just compared to you side by side. So I think there's a much broader picture here is about how to reason about statistical analysis in a multi-resource service system, like a load balancing system or multi-class queuing system. And namely, there are two big questions among many. Number one, how can you collect data? How should you collect data? Should you collect data resource by resource, asynchronously, like just collect a queue length, all the servers? Or should you collect data sort of throughout time, get a slice of the reality through time, and maybe use that to do something more clever? By the way, action data sort of fits into the synchronous version because it's driven by decisions made when the agent looks at the entire system at once and made some decision. And also, once you have the data, what type of summary statistics should you lean on? Should you lean on a marginal statistic, for example, looking at the distribution per server? Or should you look at some kind of joint statistics that kind of slides again through different resources at the same time? All right, so to be specific, here's a graphic that illustrates these different approaches. So in this example, you can actually either collect data synchronized. So here, X is time and Y is my queue. So you can see that I collect data for all three queues at this time, all three queues, and so on. Or you can visualize it differently. I just let each server collect data sporadically across time, and I don't worry about how synchronized they are. And typically synchronized is a bit more expensive. It requires like a load balancer to be involved, but asynchronous can be just logging on the server side and don't worry about it. Okay. And as far as test statistic, you have the same trade-off. You can either have each server integrates over time and compute some statistics. So here you do a kind of in parallel, or you have a joint statistic, which is you compute a function of each slice of the data you collected across server. So they'll get two different way to slice data. So in summary, we end up with three different options: asynchronous with a marginal statistic, synchronous with a marginal statistic, and finally synchronous with a joint statistic, because we cannot really calculate joint statistic with asynchronous data. All right. So with that in mind, essentially everything I've told you so far, and in fact, the formal results in our paper kind of falls into these categories, which is that we can show that, in fact, marginal statistics in general is really bad. It doesn't matter if you collect data synchronously or asynchronously. It just has this kind of a feature where under adaptive policies, we tend to get some kind of load equalization or information erasure or state space collapse, such that you just can't tell. It just does not reflect. However, if you have the luxury of synchronous samples, then you can indeed use joint statistic to do a very good job. And in our example, action data is actually a joint statistic derived from the queue length slicing at a particular time.
So Kuang, in the interest of time, now you're summarizing. Yeah, so take like 30 seconds to summarize, I would say.
Okay, so I'll summarize, but I think just maybe flash a few questions. Obviously, this talk is all about information and allocation in all different combinations. And I think this community has a lot of interesting ideas and tools to offer. And here I'm just listing some high-level questions. Basically, how should control algorithm designed with the statistical inference in mind, or should we design that with that in mind? And then maybe a more technical question for this audience is that we've seen state-space collapse playing a very key role in the performance evaluation of various policies. But so far, it hasn't been really used as a design tool for understanding sort of how do you leverage it or how do you mitigate it when designing other policies. So for one part, our result essentially shows that state-space collapse actually has a pretty big impact on performing statistical inference because it actually makes the states look very similar across different resources. So I think like that's another sort of a regime where the tools from this community can be quite interesting, illuminating. Okay, so I guess I'm out of time, and then I'll hand it back to you, Michelle.